Let us talk today about the pendulum and how the pendulum disproves conventional flat Earth ideas about gravity. Why do all objects near the Earth's surface fall to Earth? And of a special interest for us today is the question, what does make all objects fall down to flat Earth? In Spherical Earth Universe, objects fall down because of gravity. But in the conventional or typical Flat Earth Universe, there is no gravity. According to the Flat Earth Wiki, the Earth is constantly accelerating up at a rate of 32 feet per second squared, or 9.8 meters per second squared. This constant acceleration causes what you think of as gravity. Imagine sitting in a car that never stops speeding up. You will be forever pushed into your seat. The Earth works much the same way. It is constantly accelerating upwards. Well, this is the case, as I already said, in the conventional Flat Earth Universe, because actually there are several Flat Earth universes, and some of them even allow for a possibility that gravity does exist. We can read about such unusual, deviant universes in the same section little below. Yet in real-life conversations with flat earthers, I always keep hearing that gravity, that is the force of attraction between two masses, doesn't exist. To illustrate the difference between the flat Earth and the spherical Earth ideas about why objects fall down, in the Flat Earth Universe, flat Earth is constantly accelerated upward. The rate of acceleration, roughly 9.8 meters per square second, is denoted by the letter G. Because of this upward acceleration, all objects near flat Earth are like passengers in an accelerating car, and they are pushed into Earth by the force of inertia, with acceleration equal to g. On the other hand, on spherical Earth, objects are pulled to Earth by the force of gravity, with acceleration equal to g. So we have two very different explanations for g, which physicists call the free fall acceleration. G in these two scenarios is produced by two different forces. Can we determine which of the two universes we live in? Yes, we can. To do that, we will use a downright common pendulum. The rate at which the pendulum swings can be characterized by its period. The period of the pendulum is the time it takes to make one full swing forth and back, forth and back, 1 and 2. 1 and 2, forth and back, makes one period of the pendulum. Look at the top expression. 2 multiplied by the number pi does not change. If we use the same pendulum, its length L does not change either. The only thing in this expression that is left is g, the free fall acceleration. If g changes, then so does the period t. If g is constant, so is the period t. From the expression above for t, one can easily get the expression below, the expression for g. So the great thing about the pendulum is that it is an excellent scientific tool which can be used to determine g, the free fall acceleration in our vicinity. We simply have to know its length, the pendulum's length, then we swing it and time it. Now comes the crucial idea behind this whole presentation. Let us use the pendulum to measure g, the free fall acceleration, in many different locations across the planet, and compare the measurements with the two theoretical universes. On flat Earth, g must be the same everywhere, because flat Earth accelerates upward as a single unit. All parts of it have the same upward acceleration. Therefore, the force of inertia will push all objects down with the same acceleration, g, everywhere. On the contrary, on spherical Earth, g must be different in different places. And this will easily allow us to determine which of the two universes is sci-fi and which is real. So let us take a moment to discuss why g, the free fall acceleration, must be different across the spherical Earth. First of all, the fact is that spherical Earth is not exactly spherical. It's squeezed at the poles. It's oblate. Its width at the equator is greater than its height. Because of that, objects at the poles, for example, are closer to Earth's center and therefore are attracted stronger than objects at the equator, which are further away from Earth's center. It means that g will be greater at the poles than at the equator. It's quite easy to understand. The greater the force of attraction, the greater acceleration it produces. Secondly, because Earth is squeezed at the poles, objects at the equator are located further away from the axis on which spherical Earth rotates. Spherical Earth's rotation works pretty much like rotation of the merry-go-round. The further from the axis of rotation you are, the harder you should hold on, because the centrifugal force at the edges of the merry-go-round is the greatest, and this force tries to throw you away from your seat. So objects at the equator are thrown away from Earth stronger. This throwaway centrifugal force acts against gravity and therefore decreases g. At the poles, this throwaway force is zero because poles are on the axis of rotation. At the equator, the throwaway force has its max magnitude because the distance to the axis of rotation is the greatest possible on Earth. As a result, at the poles, g will be greater than at the equator. And thirdly, masses within Earth are not distributed evenly. In some places, more mass is located than in some other places. Consequently, g, the free fall acceleration, will be greater where there is more mass and smaller where there is less mass. Now we have to find out whether g changes across the planet or remains the same. If g remains the same regardless of where we use the pendulum to measure g, then Flat Earth Universe may be true. However, if g changes from place to place, then Flat Earth ideas about gravity, about why things fall down, cannot possibly be true. Instead of making our own measurements, which we could certainly do, let us use the results obtained by others. For example, Sir Isaac Newton wrote in 1687, "Now several astronomers sent into remote countries to make astronomical observations have found that pendulum clocks do accordingly move slower near the equator than in our climates. And first of all, in the year 1672, Monsieur Richer took notice of it in the island of Cayenne. Sir Isaac Newton does not say that time itself goes slower or faster. He says that the pendulums of the clocks moved slower or faster, depending on geographical location. He says that the period of the same pendulum is longer at the equator than in Europe. It can mean only one thing, namely that G at the equator is not the same as G in Europe, and the pendulum feels this difference. Let us read some more. Afterwards, our friend Dr. Halley, about the year 1677, arriving at the island of St. Helena, found his pendulum clock to go slower there than at London without marking the difference. So the pendulum have a message for us. It's an absolutely firmly established scientific fact that g, the free fall acceleration, changes across the surface of Earth. Let's read some more historical information about using the pendulum to measure the free fall acceleration. The first person to discover that gravity varied over the Earth's surface was French scientist Jean Richer, who in 1671 was sent on an expedition to Cayenne, French Guiana, assigned the task of making measurements with a pendulum clock. Through the observations he made in the following year, Richer determined that the clock was 2.5 minutes per day slower than at Paris. Let's skip down to the next underlined sentence. Since that time, pendulums began to be used as precision gravimeters, taken on voyages to different parts of the world to measure the local gravitational acceleration. Pay special attention, if you will, to the following clause. Pendulums were so universally used to measure gravity. That is, they were used by many different scientists from many different countries in great many places on the face of the planet over decades and even centuries. And those reliable, independent measurements invariably show that gravity, that is the value of g, free fall acceleration, varies across the planet. What is to be our conclusion today then? That has to do with our discussion of the Flat Earth Universe versus the Spherical Earth Universe. The conclusion that begs itself is that Flat Earth Universe is not real. It's a sci-fi universe because its physics doesn't work. In the strict sense, the pendulum experiments falsify only the conventional Flat Earth Universe, because, as was noted, there are some flat earth theorists which believe in gravity. They may rejoice today. Not for long, though. We will deal with those non-conventional flat earth theories in a separate video. We will show that their physics doesn't work either. On the basis of the pendulum experiments, we may say that only non-conventional, non-orthodox flat earth theories have passed the test. The typical flat earth theory, which denies the existence of gravity, has been flanked.